How do they go from outside the cell to inside the cell? And what do we call it? Through the cell membrane, and the system has a name. But first, why do molecules move at all? So I have a beaker of water, and I'm going to put a drop of coloring. And you can guess what's going to happen. It's going to move, but what's moving? And it's going to keep moving until it evens out. So the question is, what magical force moves it, and how does it know to go from the red to the clear? How do molecules know to go from where they're more concentrated to where they're less concentrated? How do they know that? No, this is not a DNA-based substance. This is just, it's not a cell. This is non-living material. This happens in the non-living world. So one way the cell gets molecules is through what you just saw. And that has a name, and it's called? No, close, the other one? Diffusion, yes. 8th grade, 7th grade, some grade, right? You learned about that. So, but you didn't learn it the way I'm going to tell you about it. So what makes diffusion work? Like, what makes it happen? Why do molecules spread out? So what I did is, there was a program that was, I didn't want to buy it, so I used it on a trial version, and I videotaped it. And what I did, you're going to see just now, is I put molecules, because you cannot see the molecules in the beaker. But I'm going to show you what the molecules do right now. Check this out. I like this program. It's actually a physics program, but I use it for biology. So this is how the program begins. Not important. And then I pretended the green molecules, are water molecules. We're just pretending. And the red ones are the red dye. So why do they even out? What intelligent magic is it? And it turns out it's random motion. But how can random motion be predictable? Like, I can predict you, if you put two things together and they can flow, they will flow from where they're more to where they're less. So I'm going to predict that the red molecules are going to go from the right side to the left side of the screen while I let them bounce around. Not because they're smart, but because of random bouncing. Where does the energy come from for them to move? Anyone know? How do they, a car doesn't go without energy. Where do you get energy to move? But there's no gas in air molecules, in ink molecules. How do they move around? What gives them the ability to bounce and move? What is it? Can anyone tell me?
What's up?
Heat. Heat. Now, heat energy causes molecules to bounce. Is there a place on Earth where there is no heat? And the answer is?
No.
No. Now, we're pretty smart. Can't we create an environment of zero heat? And the answer is? No. Now, we know the temperature at which there is zero heat. And that temperature is called? 0 degrees Kelvin. Absolute zero. Or negative 273 degrees Celsius. It's a super cold temperature. In a smart lab, big lab with special equipment somewhere in the world, they could get to negative 272 point something. Negative 273 is unattainable. Heat always sneaks into the system. There's always motion in the world. So let's get these guys moving. I'm going to remove the barrier, and we're going to watch. And you will see that the molecules are moving from where they are more concentrated to where they are less concentrated. Agree? The red ones are moving mostly to the left, and the green ones are moving mostly to the right. How do they know to move left and right? Random motion. Things go from where they're more to where they're less. See how they evened out? Okay, that was not intelligence. This is random motion. Random motion creates a predictable outcome known as diffusion. Molecules go from where they're more concentrated to where they're less concentrated. What is this called? What's the D word? Diffusion. Say it again.
Diffusion.
And what is it defined as? The movement of molecules from an area where there's a higher concentration to a lower concentration. Do you think it takes special powers or energy to do that? No. The energy is always in the universe. We cannot get to 0 degrees Kelvin. So the energy is always there, everywhere. It's heat energy, right? And the motion is random. You don't have to be a smart cell. You don't have to be a special system. This happens regardless. I walk in here, I have aftershave. If it's a small enough room, you get a smell. If it's a large room, you might not smell it for a while. If I walk into an elevator and I just put aftershave on, you'll smell it pretty quickly. If I walk into a classroom, you might, but they might not. And that explains something super important. Why are cells so small? Because they rely on diffusion. And if you're big, you might not get the molecules where you need them. But if you're small, like an elevator, you will get the molecules where you need them. Make sense? A big cell is not going to get molecules from outside to the nucleus in time. The cell will die by the time they diffuse that far. If this was the nucleus and I was a molecule, aftershave to get to you, that's too far. But if the cell is small, aftershave to get to him won't take too long. Make sense? And that explains why cells have to remain small. We have not evolved cells as big as a dog or a cat. That hasn't happened. Okay, next experiment. I have molecules on both sides. Actually, more on one side. It's the same story, but a little different. So, the difference with this experiment, pay attention, is that there is a membrane, an opening in a closed membrane to mimic a cell membrane. And this kind of diffusion will have a special name. Things will go from where they're more to where they're less through random motion. Yes?
Yes.
And is this intelligence? Do they figure out how many need to go on either side, do the math, and then do it? No. Random motion creates predictable results. But this kind of diffusion has a name. Somebody said it before. What do I call this? What's the O word somebody used?
Osmosis.
Osmosis. You guys know from Osmosis Jones and all that. And why do I call this diffusion osmosis? Why do they just call it diffusion? It's the same thing. What's different? They're always balancing out. That's true, but how is this different from the last picture? What do you see there? There's an opening in the membrane. So diffusion across a membrane is called osmosis. Do you understand the difference? If I take off this membrane and just run it, that's diffusion. If I put a membrane with an opening and they go across the membrane, that's osmosis. Why use a different name for something that's the same? And the reason is coming up. It has to do with how the cell suffers because of osmosis. And I want to explain that to you next. So we're going to see they evened out, correct? But here's the next problem. So what if, let me get to my next experiment. I just want to show you, not through intelligence, but just through random motion, you get predictable results. Now check this out. I created an opening, the cell membrane, pretend, right? But this time, everybody can pass, except the red molecules cannot. Let's see how smart you are. So you saw the other two models. Now we have a model where small molecules obviously can pass. Medium molecules can pass, it takes them a little longer, but the big ones cannot. Now, let's pretend this is a cell on this side, and this is the environment outside the cell. You follow? And this is the cell all going around. We're just looking at a section of the membrane. What do you predict will happen with the small yellow molecules? Will they even out? Yes, because things go from where they're more to where they're less. So which way are most of them going to go? Inside the cell or outside? Inside. Good job. Thank you. You're right. Because there's more of them, yes?
Yeah.
Outstanding. Let's get to the next concept. Blue molecules. Will they go mostly inside or outside? Inside, you're right. Because there's way more of them here than there. They're more concentrated, right? Red molecules, will they go to this side? No. So think about it. If this side has equal numbers of small molecules, equal numbers of medium molecules, and the red molecules on top of that, isn't this side getting crowded more than this side? Because think about it, I'm a car, I have to take these guys, I have to take these guys, but then I have to take these guys. This side does not. Aren't I getting crowded? I am. And that's a danger to the cell. If a cell gets crowded, its membrane is not going to be able to support the crowding. It's going to inflate, and then it's going to lyse or burst. Lyse, yeah. Not like lice, but like L-Y-S-E. It's going to burst. And we have a name for a solution that causes a cell to burst. And that name is hypotonic. So this is osmosis. If there wasn't a membrane, there would be no danger of anything bursting. Everything would equal out. This side would not be more crowded. It'd be equal crowded, yes? But because there's a membrane and these molecules cannot pass, it gets crowded. And if you're in a situation, you're a cell in a situation where you're going to burst, that situation is called hypotonic. You notice I write the O really big to remind myself, hypotonic, my cell is inflating. See how the O is inflating? Such as putting a cell in pure water. If the environment outside is pure, more pure than the environment inside, the cell's going to burst. That is why at the hospital, like when I was a kid, I went to the hospital to visit someone, and they had the bag dripping in the person's arm. You know the bag that they hang? And I was reading it because I was always like curious like that. And it said like water, sodium chloride. I was like, why don't they just give them like pure water? It's the cleanest thing. Distilled water. Why do they put all this down? And now I know, if they give you pure water, it's going to be a hypotonic solution. And the cells that are going to be in the vein, in the blood, are going to burst. So what do? They put salt in the water, like putting red molecules on this side, to equal it out so that water does not rush into the cell and burst the cell. That's why you get saline. Anybody wear contacts? Yeah. You don't wash with distilled water. Distilled water is the best. It's the cleanest. But you wash with saline. Why? Because you stress the cells if you put them in pure water. You're putting them in a hypotonic solution. They need a saline solution. Washing your wounds, if you ever get injured, saline solution is best. Why? Because you stress your cells. They become it's a hypotonic solution. They become distressed. Make sense? So let's watch what happens and see if our prediction matches this model. So will the right side, the cell, get inflated? So we'll let it run and watch what happens. Okay, so there we go. Obviously the little yellow ones are going to even out. The blue ones will take longer, but they're going to even out. But the red ones cannot. Why? Too large. The word for the red ones, things that are, if we pretend the little yellow ones are water, things dissolved in the water, the big molecules you see, blue and red, there's a name for them. They're called solutes. So the solute concentration will be higher inside the cell. And the cell bursts. And you can see it happening right there. Even if I stop it now, it already looks more crowded. And it hasn't even run that long. Can you see that? Yeah. Because the blue ones are going to even out. You were right about that. That was the correct prediction. The little water ones, the small ones are going to even out. You were right about that. And then the red ones cannot. And so this side ends up being more crowded. It's hypotonic. Let's reverse the story. Follow me on this and then we're done. Let's pretend this side is the cell. Let's just switch sides. So this is the cell, and this side is the outside environment. Can you do that for a sec? Just pretend this is the cell now. With me? This side lost molecules, is that correct? And this side gained molecules, is that correct? You saw it, right? So if this was the cell and it ended up losing molecules, the cell would actually start to deflate and that would also kill the cell. And there's a name for that solution, and we call that a hypertonic. And you notice how I drew the E to indicate a cell that is like a balloon losing air. You ever see a balloon and suddenly somebody loses the air, and then what? It looks like a shriveled up balloon, correct? That happens to cells. So let's go over the lesson. Cells placed in a hypotonic solution. Good job. Placed in a hypertonic, shrink. So is there a way that they could neither shrink nor go up? Yes. If you have the same solute concentration inside and outside the cells, then that's called an isotonic solution. And even though molecules move in and out, they move in and out at the same rate. No side gains and no side loses. There is still an exchange of molecules. It's just an even exchange, so nothing loses, nothing gains. And that's an isotonic solution, like saline solution. It's isotonic. Let me ask you a quick. I have a cell. I put the cell in a super salty solution or a super sugary solution. Let's go with bigger molecules, like the red one. So I have a cell. I put it in like very sweet water. Is the cell going to gain water or lose water? Lose. Outstanding. Outstanding. Okay, I put a cell in pure water. Is it going to gain or lose water? Gain. What's going to happen? Blow up. That's right. Okay, the very sugary solution, is that a hyper or hypotonic?
Hyper.
Hyper. Wow, you guys are good.
Because sugar makes you hyper.
Oh, because sugar makes you hyper. I like that. Sugar makes you hyper. So it's a hypertonic solution. And the pure water is what kind of solution then? Hypotonic. And just a little bit of salt equal to the cell is isotonic. And that's the only solution you can use. Doing surgeries, doing washing your eyes, wounds, whatever. It has to be isotonic. Make sense? And those three things are a study of osmosis. So osmosis is the movement of water across a semi-permeable membrane. By semi-permeable, I mean some things can pass and some things cannot. And that's called semi-permeable. If it was completely permeable, it would just be called a permeable membrane. If everything could pass, it's just permeable. If only some things can pass, it's semi-permeable. Questions? We good?
Yes.
Okay. Outstanding.